To find the domain of a composite function, we follow a two-step process. The definition of a composite function is that the g function is plugged into the f function, and therefore any element that's plugged into the f composed with g function would have to pass through g first. So the first thing that we're going to want to do is find the domain of that inside function. We must get a real output from g to serve as an input for f. From that domain, we would then exclude any additional values that would cause the output of g to be the domain restriction of the outside function f. In other words, we're going to figure out which x value causes the output of g to be the restriction of f, and then we would exclude that quantity. So let's look at an example. First, we'll find the composite function, f composed with g. And this means we'll start with the f function on the outside and then plug the g function into that. So f composed with g is going to begin with the f function, but we leave holes for the independent variable x. So we have x over x plus 3. And now into those independent variables, we'll plug the g of x function. G of x is 2 over x, and so we put 2 over x into both of those spots. Now this is what we call a complex fraction, and by that we mean complicated, not imaginary. A complex fraction has more than 2 levels, and we always want to simplify a complex fraction being down to just 2 levels. Now, since we have functional notation on the left-hand side, we need to operate entirely on the right-hand side. We don't want to do anything to both sides of this equation. We don't want to mess up the functional notation that's on the left. So staying entirely on the right-hand side, there are a couple things we can do, one of which is that we can multiply this fraction by what I like to call a well-chosen 1. Multiplying a fraction by 1 is not going to change the value of the fraction, but we want to choose this 1 carefully to be something that benefits us, and the 1 that we choose is going to be the least common denominator of the entire fraction. We'll look at all the denominators in the top and the bottom, and we'll multiply by the LCD over the LCD, which of course will be equal to 1. The only denominator in the top and the bottom is x, and so x is the LCD over this entire fraction, so we'll multiply the top by x and the bottom by x, which of course is equal to 1 and therefore won't change the value of the function. Before we multiply, I'm going to do a little bit better and call that top x, x over 1, as well as the bottom, because since I'm multiplying into a fraction in the top and a fraction in the bottom, this is going to help me to make sure that my x's cancel out appropriately. In the numerator, we see 2 over x times x over 1, and these two x's clearly cancel out now, so now I have just 2 over 1 in the top, which is going to be 2. In the denominator, we need to make sure that our x is distributed into the parentheses correctly. So we'll say 2 over x times x over 1 here. The x's are going to cancel, and I'll end up with just a positive 2. And then when I distribute the x into the second term, we have 3 times x, which is 3x. Now we have a 2-level fraction, which is an acceptable answer for our composite function. Now in part B, we're asked to find the domain of this composite function and write our answer in interval notation. Now as we saw, this is a two-step process, and the first thing that we want to do is find the domain of the inside function, or the function that acts on a potential domain element first, which in this case is g. Remember, if we plug a domain element into the f composed with g function, it is the g function that would operate on that element first. Notice this is our g function, and the only domain restriction that g has is that x cannot be equal to 0, so we'll just make a note of that domain restriction. Now the second part is the tricky part. In the second step, we want to set the g of x function equal to the domain restriction of f. The outside function is f, and we see that f cannot have an input of -3. So we want to figure out who is the element that passes through g to become the -3 that's not allowed as an input for the f function. And that would have to also be left out. So we take our g function, which is 2 over x, and we say which x value causes that output to be 3. Now solve for x. This is a rational function, so we can multiply both sides by the LCD, which is x over 1. So x over 1 times 2 over x on the left is just 2, and the right-hand side is -3x. So what we see here is that x is equal to -2/3 must be an additional domain restriction, And then we take the two domain restrictions together to write the domain of the composite function in interval notation. So the domain begins with negative infinity and goes to negative 2/3. Leaving out negative 2/3, we go to 0. Leaving out 0, we go to positive infinity. Now before we leave, let's take a closer look as to why negative 2/3 had to be excluded. Let's recall that f and g were these functions, and what we said was that negative 2/3 is not a domain element or is not an allowable input for the f composed with g function. One way of evaluating that is to take negative 2/3 and plug it into the g function first, and then that output goes into f. So what is g evaluated at negative 2/3? We plug negative 2/3 into our g function, and this is a domain element for g. It doesn't cause the output to be undefined, but what it does cause the output to be, after we multiply by the reciprocal of the denominator, is negative 3. And when we try to plug negative 3 into the f function, now we can see why that is a problem. Negative 3 causes the f function to be undefined, and the domain element that we started with was negative 2/3. Negative 2/3 is the element that passes through the g function to become the domain restriction on the f function, and that is why it's not part of the domain.